Hello everyone, welcome to our discussion of section 9.3 where we will be talking about polar coordinates. Now some of the stuff we will discuss in this section you've already seen as part of Pre-Calculus 2 or Math 127 if you've taken the course here. And some of it is going to be specifically geared toward calculus topics. So we will begin with the basics of polar coordinates. You're already familiar with the Cartesian coordinate system, or otherwise more popularly known as the XY coordinate system. So we know that if we want to locate a point within the XY plane, we will have to have an X and a Y coordinate for that point. The other thing we should know in respect to polar coordinates that we're going to discuss in a few seconds is that each coordinate, each XY coordinate is unique for that point. There are no other coordinates for that point. But when we switch over to polar coordinates, not only X and Y are gone, instead we have R and theta, R being the length from the distance from the origin to that point in any quadrant, comma theta, which will be the angle from the positive side of the x-axis, but also is that this coordinate, whatever it may be, whatever r and theta may be, there are many other equivalent coordinates in polar form for that same point. So for the XY or the Cartesian coordinate system, we only have one unique coordinate, a set of coordinates for one point. But in the polar coordinate system, we have many different looking polar coordinates for the same point. Okay, and r is again that distance from the point to the origin, and then the theta being the angle between that distance and the positive side of the x-axis. Now in this figure, we're identifying some of the terminology associated with the polar coordinates. First of all, that's what it's called, polar coordinates. But this positive side of the x-axis is called polar axis. And theta represents that angle between the polar axis and the distance between the origin, from the origin to that point. And the origin is called the pole within the polar coordinate system. Okay, theta, this angle between the polar axis and the distance from the origin to the point we're identifying with polar coordinates. Theta is positive if measured counterclockwise. So if I put an arrow here, and I don't want to do that in this case because I want to keep the figure general. If we are going to this line from the polar axis, or we're going counterclockwise, the theta value is going to be positive. Let's say pi over 4 or pi over 3. But if we get to this line in the clockwise manner, going from polar axis this way to that line, that theta will have a negative value. Okay? And 0 comma theta, that is when r is equal to 0, represents the coordinates of the pole, that point. And it doesn't matter what the theta is, because if r is 0, then we're on that point. In other words, I might even add that here, that is 0.0 comma theta, the origin. Okay? Now, an important, I just mentioned that in the polar coordinate system, for the same point, we have many different representations of the coordinates, right? We just mentioned that. Now, one way to achieve these many different forms of the polar coordinates for the same point is using negative r values. So if that happens, the interpretation of that is that suppose we have a point with polar coordinates r comma theta, right? Theta being that angle from the polar axis to that line, from the pole to that point. Now, if we have a point such that the theta stays the same, but the r value changes to something negative. Let's say if this was 2 comma pi over 4, if we switch that to minus 2 comma pi over 4, right? So the r becomes negative from 2 to minus 2. Now, the interpretation of that in the polar coordinate system is that that point is exact on the same line on the opposite side of the original point. So minus r comma theta would be here, whereas r comma theta was on that. This is always the case. If you take a polar coordinate and make the r negative value, then what you've done, you've moved that point to the opposite, on the same line, to the opposite side. Okay? And the other one way to achieve that would be take the theta for the original point, or for the original polar coordinates, and add pi to it. So we simply go counterclockwise, adding pi, and we get to that point. Okay? We will do some examples on these so you'll know exactly how this works. And this is basically a description of what I just said, that any pairs of points with coordinates such as this and that lie on the same line. That's the important thing to remember. Through the origin, and they are the same distance from the origin but on the opposite sides of the pole. Okay, and this is just another way of saying that same thing. Minus r comma theta equals r comma theta plus pi. And this is, again, is just for the sake of your notes. I've written down that in the xy plane, every point has only one unique set of coordinates, but in the polar coordinate system, each point has many coordinate representations. Okay. So if we are asked to find other polar coordinate representations for the same point, the first thing we want to do is graph the current polar coordinates. So whatever polar coordinates you've been given initially, graph it. Identify where that point is within the quadrants, the first quadrant, second quadrant, and that. And the second thing is use minus r or r in combination with theta plus or minus pi, or theta plus or minus 2 pi, to find other coordinates for the point. So here's our first example. We are asked to plot the point, which is good because even if they didn't ask this, we should do it anyway. Plot the point whose polar coordinates are given, then find two other pairs of polar coordinates of this point. For the same point, we want to find two other pairs of polar coordinates. One with r value positive, and one with r value negative. Okay? So we're going to do that with this point, polar coordinate. And the first thing, of course, I'm going to do is take my own advice and graph this point. So we want to know where this point is within the plane. Okay. So 1 is some distance and is positive, and then minus 3 pi over 4. So because this is a negative, we are going counterclockwise. We are going clockwise, right? That's what we mentioned in the first page here. For theta positive, which is not what we have negative theta, right? That's our theta, right? So this is r comma theta we've been given. So theta is negative, not positive. If it was positive, if it's measured counterclockwise from the polar axis. If theta is negative if measured clockwise from the polar axis. So because it's negative, we need to find this angle, we need to go in the clockwise manner. So this, we're going to start from the polar axis, right? This is our polar axis. Because it's negative, I'm going to start from the polar axis and go clockwise. Because this is less than 4 pi over 4, which 4 pi over 4 would get me to this point, to this line. But it's less than that, right? It's minus 3 pi over 4. So I'm going to be in this quadrant someplace. So I'm going to just put a point here and connect it to the pole or the origin with a line, and identify that point as 1 comma negative 3 pi over 4, and just supposing that r equals 1, that distance is from the pole to that point is just 1 whatever unit. Okay, so this is what we have, and we need to find. So first we plotted it, which is what they asked us to do. And now we need to find two other pairs of polar coordinates of this point, one with r equal greater than or positive and one r negative. So the easiest one to find is just this one, because we already have r positive here, right? So we can just keep that. So we can do the coordinates with r positive or r greater than 0. So I'm going to keep that 1. So I want to give an equivalent, I want to create an equivalent polar coordinates for the same point. And the easiest way to do it is go 2 pi, right? So this angle and then that plus 2 pi. So I'm just going to go around 360 degrees and end up on the same spot. So let's do that. So minus 3 pi over 4 plus 2 pi. So then we have 1, and then common denominator is 4, and then we have minus 3 pi plus 8 pi. Okay, so we can simply 8 pi minus 3 pi is 5 pi over 4. So this point is going to be equivalent to that original polar coordinates. It'll bring us back to this point. Okay. So now let's find this one, an equivalent for this polar coordinates with r less than 0 or negative. Well, because of this r being negative, all I'm going to do is change this from positive to negative. Minus 1, comma, minus 3 pi over 4. Right? If I just stop there, what have I done? If I just make this negative and keep the theta angle the same, what have I done? Well, what we've done is just put this point along the same line on the opposite side. That's what we were saying earlier, right, on the previous page, that if you just change the r to negative r for the same angle, what you've done is move the point 180 degrees to the other side. It's going to be on the same line, but it's going to be on the opposite side across from the pole. So that's what I've done. Simply by putting a negative in front of that, I moved this point to that side. So now this coordinate, if I leave it alone, is it going to be equivalent to this? No, because it's going to be on this side. not on this point, right? So I want to bring, right now I'm here. I want to bring it back to this point. So all I have to do is add or subtract pi, right? Or 180 degrees. Whether you add or subtract pi has to do with your preference, whether you want to move counterclockwise, which would be plus pi, or clockwise, which would be minus pi. It makes no difference. You're just going to find two different equivalents of the same point. So in this case, I'm just, since I said plus 2 pi for this one, I'm going to say plus pi for this one. To bring the, right now, the point is here, and I want to bring it back here, so I have to add pi to it. If I had done minus 2 pi, I would just be consistent and say minus pi. Okay, so let us clean this up a little bit. So we have minus 1, common denominator being 4, minus 3 pi, and then we have 4 pi there, right? And then we have minus 1 comma, that would be pi. 4 pi minus 3 pi is just pi over 4. Okay. So we found two pairs of coordinates for the original polar coordinates, one with r greater than 0 or positive, one with r negative here. Okay. Let's do another example. So the first order of business is plot this. Even if we're not asked to plot this, let's plot it, because it's going to help us understand better where we are within the polar coordinate system. Okay. So now we have that. Okay, so 1 is positive, and then 7 pi over 4 is, where do you think this is? Which quadrant? So notice that if this was 8 pi over 4, where would we be? 8 pi over 4 would be 2 pi, right? After simplifying. 8 pi over 4 would be 360 degrees, 2 pi. We would go, and because this is positive, we would go counterclockwise 2 pi. We would be back on the x-axis. From the polar axis, go counterclockwise back to the polar axis. But this isn't 8 pi over 4. It's a little bit less than that. And because we're moving counterclockwise, because this is positive, we're moving counterclockwise. So which quadrant do you think this should be? If it's a little bit less than 2 pi, it would be right here, right? We would be in the 4th quadrant. So let me plot a point there. We were somewhere there. So r, which is 1, would be that distance from the pole. Oops, sorry. So this is r equals 1, and the angle we're talking about is from the polar axis here, going all the way around like that, and this theta is positive 7 pi over 4. Positive, we're going counterclockwise. If this was negative, we would have to go clockwise. Okay, so now that we know where the point is, let's again start with finding an equivalent polar coordinate for this such that r is positive. So I'm just going to keep this as it is. So for r greater than 0, we have 1 as it is. Now, I can either, since I kept the r positive as it was, I can get to this point either by subtracting 2 pi from this, which would mean I'm going clockwise, so I'll be going clockwise this way back to this point, or I can add 2 pi to this, which means I would go 360 degrees in the counterclockwise direction. It makes no difference. The result is the same. We did add 2 pi or pi in the previous example. We added. Let's subtract this time because it makes no difference. So 7 pi over 4 plus, oh, sorry, I meant to subtract, minus 2 pi, right? So this will be equal to, let's clean this up. We have common denominator 4, 7 pi minus 8 pi, and so we have 1 comma minus pi over 4. Okay. So we found an equivalent polar coordinate for that such that r stayed positive. Now let's find another pair such that r is negative. So as soon as we write this condition, I'm going to switch over to negative. So I'm going to make this negative 1 comma 7 pi over 4. If I stop there and put my parenthesis, what have I done? What I've done is move this point along the same line to this side, right? That's the effect of changing r from positive to negative, or vice versa. It'll move the point 180 degrees to the other side across from the pole. So right now, if I stopped, am I here? No, I'm going to be here. Do I want that? No, I want to be back here after switching to r negative. So all I have to do is either add pi, which would be going counterclockwise, or subtract pi, which would be going clockwise back to the point where I started. So here I subtracted, I'm going to subtract pi. Since I don't want to be here after making this negative, r negative, I don't want to stay here, I want to be back to the point where I was. So subtract pi, which means I moved clockwise, in the clockwise direction, back to the original point. Okay, so now we can do the rest of this. Minus 1, and the common denominator 4, so we have 7 pi minus 4 pi, right? Like that. And then what do we have? We have minus 1, 7 pi minus 4 pi. We have 3 pi over 4, and that's that. So we found an equivalent polar coordinate to this coordinate such that the r is now negative. Okay. Let's do this example. We've done a couple of examples I forgot to mention. Please pause the video. I hope you remembered and to do that. So I strongly encourage you to please pause the video, answer this question on your own. Plot this first of all, and then find two equivalents to this, one with r negative and one with r positive. Okay, so hopefully our answers agree. Okay, so we want to plot this. Even though this is negative 3 comma pi over 6, the first thing I'm going to do to get this right is I'm going to plot positive 3 comma pi over 6. So first, let us plot 3 comma pi over 6. So whenever you're given a polar coordinate with negative r, first plot the one with positive, and then move across the pole to identify where this point is. So 3 comma pi over 6. Pi over 6 would be going, this is positive, so we're going counterclockwise this way. So this point, it's going to be somewhere here. And I'm going to show it with a, and this is 30 degrees. So I'm just going to show it like that with dashed line connecting to the pole, not with solid lines. Right, so this is where that point is located. So 3 comma pi over 6. Now our point is minus 3 comma pi over 6. So we're not there yet. So all we have to do to get that is just move that point across the same, on the same line across the pole. So our point is located along that line in this quadrant, the third quadrant. We're right here. Okay, so this is minus 3 comma pi over 6. Okay, so now that we have that, let's see how we're going to find the other equivalence. So see, we can find the positive one first by taking, let's see, so we can take, let's see, so negative 3 if we are here. So for r greater than 0, right, so we have negative 3. If we want to, so as soon as I make this positive, right, 3 comma pi over 6, what have I done? I've moved this point to that spot. Is that where I want to be? No, I just want to be here, but I want a different polar coordinate for that point. So now, since I moved from negative to positive, with the angle kept the same, I'm back, I'm here. I want to be here, right? So I can just either add pi by moving counterclockwise or subtract pi by moving clockwise. It makes no difference. So I'm just going to add or move counterclockwise back to the point where I started. So plus pi. Okay, so then we have, so we have 3 comma, common denominator, we have pi plus 6 pi, and simplify things there, we have 7 pi over 6, right? So this is a polar coordinate equivalent to that, such that the r value has become positive. Now let's do another one with r staying negative as we started with. So r less than 0. So we're keeping the same, minus 3 comma pi over 6. Can I stop now? No, because this would be identical to that. I want to find an equivalent to that, so I have to do something more. Well, the easiest thing to do, since we kept r negative as it was, we can just go around 2 pi. Now we can add 2 pi by going counterclockwise back to this point, or we can go minus 2 pi, which would take you in the clockwise direction back to this point. It makes no difference. I added pi to get the positive. I'm going to add 2 pi to get this polar coordinate. So then we have minus 3, common denominator. We have 12 pi here. And then, of course, we have minus 3 r value. And theta will be 13 pi over 6. Okay, and here's an equivalent polar coordinate to that, such that r stayed negative. Okay, all right. So now that we're discussing polar coordinates and Cartesian coordinates, is there a connection between them? Yes. So here are formulas, some formulas that will establish that connection for us between polar and Cartesian coordinates. So if we want to obtain, if we have polar coordinates and we want to obtain the Cartesian coordinates, we simply take r times cosine of theta and we get x, take r times sine of theta, we get y. And this picture is just showing you a justification for this transition. So if we have this point with polar coordinates that and Cartesian coordinates, xy coordinates like that, and r is this distance, notice that this distance from here to here is y, from here to here is x coordinate. Now you know that if you take the cosine of theta, from trigonometry we know this, cosine of theta is equal to the adjacent divided by the hypotenuse, right? So adjacent is x and divided by hypotenuse, x over r. And then we want x, cross multiply, we get x equals r times cosine theta. Now sine of this angle is the opposite divided by the hypotenuse, and this being the right triangle that we have. Right? So from trigonometry, we know that sine of this angle is the opposite divided by the hypotenuse. Opposite being y, hypotenuse being r, and then we can solve for y. We have r times sine theta. Now, if we have been given Cartesian coordinates and we want to obtain polar coordinates, we use this set of formulas. So this is to obtain, to obtain Cartesian coordinates from polar coordinates. I just shortened it so that it would fit. And here, to obtain polar from Cartesian coordinates. Okay, so we'll use this. You have x and y, you simply square them and add them, and then for r, obviously we would take the square root of both sides, and r being positive, a distance, so we would just accept the positive and toss out the negative one, and tangent of theta is equal to y over x. And of course, theta is the inverse tangent of that quantity, right? But this is where the main formula, tangent theta is equal to y. Looking at the figure, you can see that tangent of theta equals the opposite divided by the adjacent, y over x. And then for theta, we would calculate the inverse tangent of that quantity. Okay. All right, so in this example, we want to find the Cartesian coordinates of this point. So in other words, these are the set of these two, the highlighted ones, are the ones we're going to use. For x, we set it equal to r cosine theta. For y, we set it equal to r sine theta. One thing I want to quickly mention is that notice that these formulas, we're going to use them in some way to convert between Cartesian to polar coordinates, or from polar coordinates back to Cartesian. And also we're going to use these in conjunction with finding equations, entire equations. So we'll be doing two kinds of examples. One kind of example is to convert the coordinates of a single point from Cartesian to polar, or polar to Cartesian. The other main kind of problem we will deal with is finding entire equations, not just for a point, but entire equations for a line. So if the equation of a line is being given in Cartesian form or XY form, we want to convert it to polar form. Or if the entire equation is being given in polar form, then we want to convert it to Cartesian form. Okay, so just be aware of those two main types of examples that we will be working on. It's not just points that we convert polar and Cartesian coordinates to back and forth. We have entire equations, curve equations that we can convert back and forth between polar and Cartesian forms. Okay, but in this case, this is a point. See, this is a point, not an equation that we're looking for. So we're just going to use these two equations. So for x, we know x equals to r cosine of theta. And so r in this case is 2 cosine of minus 2 pi over 3. And cosine is an even function. So because it's an even function, I can write this as 2 cosine of 2 pi over 3, right? Because cosine is even, cosine of negative angle and cosine of positive that same angle are equal. And then, so this is, let me actually, it's good, even though they didn't ask us, it's always good to plot these points to see where they are. So I'm just going to quickly draw a little plot here. Just a little plot. So 2 comma minus, notice that this angle is negative, so we're moving in the clockwise direction from the polar axis. So it's negative, that, and it's a little bit less than minus 3 pi over 3. This is important to notice because minus 3 pi over 3 would put us right on this axis in here. But it's less than that. Moving clockwise, less than that, we end up in the third quadrant. So this point is somewhere here with r, or 2, being the distance from the pole from this point to that point. And of course, the angle that we traced, because it's negative, it's going in the clockwise direction from here to here. So this is theta equals minus 2 pi over 3, and this is r equals 2. And I don't know why I drew that dashed. It should have been a solid line, so let me make that solid line like that. Okay, so cosine of 2 pi over 3 in the second and the third quadrant, cosine is negative because cosine represents the x-axis in these two quadrants. So we will have from the table of special trigonometric values that we learned in Math 127, and I just taught a trig class last semester, so I remember that should be minus 1/2. So this would be 2 times minus 1/2, or so we will have minus 1. Okay, so that's the x coordinate for the Cartesian system, coordinate system. So let's find the y coordinate. So y is r equals, again I'm using this pair of equation, y is equal to r sine theta. Okay, so then we have 2 times sine of minus 2 pi over 3, and because sine is an odd function, whatever that angle, if it's negative, that negative can be placed in front. So we can say minus 2 sine of 2 pi over 3. Sine of 2 pi over 3, this will be in the second quadrant. It's going to be positive, so minus 2 times square root of 3 over 2. Again, I remembered all this because I just taught a course, trig course. If you don't brush up on that, anyone, including myself, I would forget. But fortunately, it's still fresh in my mind. So then we have minus 2 and the 2 cancel out. We end up with minus square root of 3. So this is our x. Let me just put, this is our x, this is our y. So then from here, we can say that the Cartesian coordinate is minus 1 comma minus square root of 3. Okay, does this make sense given our picture? Yes, because the x-axis we're on the negative side, the y-axis we're also on the negative side. Okay, let's do another example. Okay, just like before, I encourage you to please pause the video and do your own work on this and see what you come up with for the Cartesian coordinate for this point. Hopefully our answers agree. Just like before, the first thing I'll do is just draw a quick graph of where this point is located within the plane. So notice that this is a negative R value. So what I will do is I will first plot the point with positive R values. So first plot positive 2 comma 3 pi over 4. But I'll draw this in the background with dashed lines, and then I will locate this with solid line. So 2 comma 3 pi over 4. 4 pi over 4 would put me at pi, right? 0 pi. We would put me here. This is a little bit less than that, 3 pi over 4, so I must be here for this one, not for the original one. So somewhere here, 3 pi over 4. This is 2 comma 3 pi over 4. But that's not where I want to be. I want to be minus 2 comma 3 pi over 4. So we know that if the angle stays the same, we change the R value from positive to negative, we're going to be on the same line opposite the pole. So if I put a dashed line here from this point, in the background, dashed line here, and then for our point here, we're going to be in this quadrant, fourth quadrant. We're going to be here, and I'm going to mark it with or label it with proper or the coordinates we have, minus 2 comma 3 pi over 4. Okay. Notice that this angle is positive, so it means to get to this point, we must have started from the polar axis and gone counterclockwise. So the traced angle is this angle, this angle, which is theta equals 3 pi over 4, positive 3 pi over 4. Okay, so that's just to get a feel for where this point is located, but our main objective is to find the Cartesian coordinates for this point. So we're going to use the formula x equals r cosine of theta, right? And then r is minus 2 cosine times cosine of 3 pi over 4. Of course, we know that now this is just, again, just to get a feel for where this point is. But when you make these calculations, just deal with these numbers. So cosine of 3 pi over 4, this is in the second quadrant, this quantity, not that picture. That's why I'm afraid that I might confuse some of you. I hope not. But this is just to get a feel for where this point is. But when you make the calculations, just look at this. Don't look at that. 3 pi over 4 is in the second quadrant, and where cosine is negative. So minus 2 times minus square root of 2 over 2. So then 2 and 2 cancel each other out. Minus times minus is positive square root of 2. Okay, so this is our x. For y, we have r sine of theta. R again is minus 2. And sine of 3 pi over 4. In the second quadrant, sine is positive, square root of 2 over 2. So we have minus 2 times square root of 2 over 2. And so these the 2's cancel out. Minus times that, we get minus square root of 2. So the Cartesian coordinates are, so x is square root of 2 and y is minus square root of 2. Now, this Cartesian coordinate, does it make sense with respect to the location of that point? Yes. So x is positive, y is negative, right, for that point. I hope this agreed with what you had solved for on your scratch paper. So here's another example. Please take the time to, or pause the video and take the time to solve this on your own. Find the Cartesian coordinate for this on your own. Let's see if our answers agree. While you're doing that, I'll go about drawing this, a rough plot of this point. Notice the r is negative again. So what I will do, the first thing I will do is I will plot this point with r positive. So once again, I will write first plot positive square root of 2, 5 pi over 4. Okay. So notice that 5 pi over 4 is a slightly larger than 4 pi over 4. 4 pi over 4 would put me here, moving in the counterclockwise direction from the polar axis. But this is a little bit larger, so it's going to be in the third quadrant, this point, not the point we have. So I will, just like last time, I will draw this in the background with dashed line. And so like that, and this is square root of 2, 5 pi over 4. Like that. And then, of course, I will continue it to the other side, because negative square root of 2 comma 5 pi over 4 is on the same line on this side across the pole. So we're here, This is minus square root of 2 comma 5 pi over 4. Okay, and the angle, of course, because it's positive, so to get to this point, then we have gone in, let's see, so we started from the, let's see, so this is 5 pi over 4. Yes, so I'll just put the theta because it's positive anyway. But this is since with an r negative, this is why I always draw the coordinate, polar coordinate with the positive r, so I don't get confused when I draw that. But the angle is positive, so I'm just going to put that as theta. Okay, but it's not. This is not equal to 5 pi over 4. This is 5 pi over 4 would be from here to that, and then of course because we have r negative, it tosses it back that way. So let me do that. It's better if I draw it here. So this is the angle, but then because of r being negative, we're not here, we're here. Okay, so this is theta equals 5 pi over 4. Okay, so now we want to, this is just to get a visual sense. Now we want to find x and y. So x is r cosine theta. So we have minus square root of 2 as r, and then cosine of 5 pi over 4. 5 pi over 4, now forget about this picture, but 5 pi over 4 is in the third quadrant. In the third quadrant, cosine is negative, so, and that would be negative square root of 2 over 2. And so we have minus positive, square root of 2 times square root of 2 is 2 over 2, or equal to 1. Okay, so this is our x value. And then for y value, y is equal to r sine theta. So this would be, r is minus square root of 2 times sine of 5 pi over 4. And then in the third quadrant, sine, of course, is negative, right? In this quadrant, sine is negative. So we have minus, again, square root of 2 over 2. And again, we get 2 positive 2 over 2, or 1. So this is our y coordinate. So we have our x, we have our y, and the coordinate is 1, 1. I know my drawing is definitely not to scale, but looking at this coordinates and where the polar coordinates were, do they make sense? Yes, they do, because this is in the first quadrant, that's in the first quadrant. All right, so let's do, now that we've done a few conversions from polar to Cartesian, we want to go the other way. So given Cartesian coordinates, we want to find the polar coordinates r theta of the points, then find an equivalent polar coordinates in the form this. So here we have to not only convert the xy coordinates to polar coordinates, but once we have this, we're going to have to find a coordinate or r that is negative. An equivalent for this where r is negative. Just keep that in mind. Okay. So we have to do a little more than the previous set of examples. Okay. So the formulas that we had, maybe I should just refresh your mind. It should be right here. So these are the formulas for converting to obtain the polar from Cartesian. Okay, just remembering that theta would be the inverse tangent of that. All right. So we have r squared is equal to x squared plus y squared. So we're looking for r. So we're just going to take the square root of both sides. 2 squared plus minus 2 squared, right? That. X squared plus y squared. And we get, what do we get? We get 4 plus 4. We get square root of 8. Square root of 8 is 2 cubed. Square root of 2 cubed, which would be 2 square root of 2. Okay. Now, this is our r. Now, let's find the angle. So, tangent, we know that tangent of theta is equal to y over x, right? In this case, y is negative 2 and x is 2. So we end up with negative 1. Now, if tangent of some angle is equal to negative 1, I mean, if this was an awkward number, I would use my calculator to get the theta in radians or degrees, in radians probably. I would get it for this problem. But this is an easy angle. We know that sine of pi over 4 divided by cosine of pi over 4, which would be the tangent of theta, is equal to 1. So this is negative. So we have to be in a quadrant where at least one of those, the sine or the cosine of that angle is negative. And that would be, so that would be in fourth quadrant. Yes, so in fourth quadrant, the cosine is positive, cosine being the x-axis, and the sine, which is the y-axis, is negative. So theta is equal to minus pi over 4. Okay, so combining these two, that one and that one, we have the polar coordinates are r 2 square root of 2, comma, minus pi over 4. So, of course, we now have to find an equivalent angle to this, equivalent polar form. So finding an equivalent polar coordinates, we have, so that means with r switch to negative. So what I'll have to do is make that negative, and I will do that minus 2 square root of 2, comma, minus pi over 4. Can I stop at this point and put my parenthesis? No, right? I just made this negative. So what I've done, if I stop here, what I've done, I've moved this point 180 degrees across on the same line on the other side. So do I want to stay there? No, I want to be back to this point. To do that, I can either add pi or subtract pi. Adding is less problematic, I guess, or easier than subtracting. So I'll just add pi, meaning I will move 180 degrees in the counterclockwise direction to go back to this where this was. Okay, so we have minus 2 square root of 2, and then we have common denominator minus pi plus 4 pi equals minus 2 square root of 2. We have 3 pi over 4. Okay, so that's an equivalent polar coordinate with r given as negative. Okay, so go ahead, pause the video and find the Cartesian coordinates for, find the polar coordinates for this, and then also find an equivalent polar form such that r is negative. Okay, so in the end, I hope our answers agree. So I'm just going to find r again first. So square root of x squared plus y squared. So what do we get? We get square root of 3 squared is 3 times 3 squared is 9. 3 times 9 is 27 plus 9. We get square root of 36, which is 6. Okay. Then we know that tangent of theta is equal to y over x. And y in this case is positive 3. X is 3 square root of 3. So this will simplify to 1 over square root of 3. Of course, we want to rationalize this. So let's multiply it by square root of 3 over square root of 3. And we get square root of 3 over 3. Again, if this was an awkward number, I would use my calculator to find the angle in radian. But this is from the table of special trigonometric values that we studied in Math 127. This is just the tangent of, if the tangent of any angle is that means the angle is pi over 6. So if tangent of theta is equal to square root of 3 over 3, therefore the angle is equal to pi over 6. So we have the r value, we have the angle value, and together they will be the polar coordinates, 6 comma pi over 6. Okay, so now we want to find an equivalent polar coordinate to this such that the r is negative. Okay, so let us do that here, finding an equivalent polar coordinates. Okay, so what I will do is make that negative, minus 6 comma pi over 6. If I put my parenthesis there, what I have done, I've moved this point 180 degrees to the other side of the plane. But I don't want to do that. I want to find an equivalent polar coordinate for this. So because by putting the minus in front of r, I am 180 degrees off. All I have to do is either add or subtract pi to get back to where I was, given that my r now is negative. So I will add pi to this to go back to where I was. So this is minus 6 comma 6, and then pi plus 6 pi. And so we have minus 6 comma 7 pi over 6. Like that. Hopefully this agrees with what you had done on your own scratch paper. Okay, so as I said earlier, this conversion between coordinate systems doesn't just happen with respect to points, it also happens with respect to equations. we can convert entire equations from polar form to Cartesian form and back from Cartesian form to polar form. And that's what we're going to do next. Okay, so here we want to find a Cartesian equation given polar coordinates. All right, so find a Cartesian equation for the curve and identify the curve. Identify the curve meaning say what is it? Is it an ellipse? Is it a straight line? Is it a circle? What is it? That's all they're asking us to do. Okay, so here we have some information given to us in terms of theta. In the polar coordinate system, the equation that we have that has anything to do with theta is this. Tangent of theta equals y over x, which we used just now, right? So now we know that theta is pi over 3. So let's substitute for theta. We have tangent of pi over 3 equals y over x. Okay? This is an easy angle. As a matter of fact, it's one of the angles shown or described in the special table of trigonometric values, pi over 3 or 60 degrees. We know that tangent of pi over 3 is the square root of 3. So square root of 3. When I taught trigonometry, I asked my students to memorize that. Not just the tangents or cotangents, the sine and cosine, because if you know sine and cosine in memory, then you can calculate all the other functions. The secant, cosecant, tangent, cotangent, all the other ones can be calculated if you know the sine and cosine for these special angles. Anyway, so this is square root of 3 equals y over x. And so we can then solve this for y. Y equals square root of 3 times x. So they ask us to identify this curve. This is just a straight line going through the origin. Now, if x was under the square root, then that would be different, right? Then that would not be a straight line. But this is outside, so this is just the slope of a straight line going through the origin. So a straight line through the origin. Okay, so here's another one. So notice here we converted an entire equation in polar form to an entire equation in Cartesian system. Okay, not just points can be converted, but also entire equations. So here's another example. Please pause the video and see how far you will get, and hopefully our answers agree at the end. All right, so the first thing I will do is whenever I see tangent theta, secant theta like this, I'd like to convert them to cosine and sine because those are easier to manipulate. And we have properties for sine and cosine that make manipulation, simplifying this easier. So plus the fact that we have x, since we're converting this from polar to Cartesian, we have equations that connect x to cosine and y to sine. So all the good reason, many good reasons we have to convert these two to cosine and sine. So let's do that. So we have tangent of theta will be sine of theta divided by cosine of theta times, of course, secant theta. Secant is the reciprocal of the cosine function, so 1 over cosine of theta. So then we can, this would result to sine theta divided by cosine squared theta. Okay. Now let's multiply both sides of this equation by r. By r, what do we get? We get r squared on this side and r sine theta on the other side. So r squared equals r sine theta divided by cosine squared theta. Okay. So now let's cross multiply, or multiply both sides by cosine squared theta. Either way you want to think of this. So we'll get r squared cosine squared theta equals r sine theta, right? Then notice that we as much as possible, we want to write this equation in terms of r times sine theta or r times cosine theta, because then those two are equivalent to y and x respectively. So this side is okay, but this side is not. But there is something we can do, right? R cosine theta squared we can do, right? We can put the exponent on the outside because it's equal, and then set that equal to r sine theta. Is this helpful? Yes, very much so. Because now what we have on the inside, r cosine theta, is x. So what we have on the left side is x squared equals, the right side is just y. Okay? Or the other way we naturally write this is y equals x squared, right? And we are very familiar with this quadratic equation that has its vertex at the origin, and it opens upward because it has a coefficient of quadratic term which is positive. Okay, so since they asked us to identify the curve, let's do that. So this is a parabola. With its vertex at the origin, and that opens upward. Okay, here's that. Okay, so now let's go the other way around. Let's go, if we have a Cartesian equation, right? If now we have a Cartesian equation, we want to go and find the polar form for this. So finding a polar equation given the Cartesian equation. Okay. Okay, and this is just something I said earlier, that the conversion between the coordinates, it doesn't happen just for points, it also happens for entire equations. That's all. Okay, so taking a look at this, we know that x in polar form equals r cosine of theta, and y in polar form equals r sine of theta. So just let's replace for y and x. Okay, so we're gonna, so let me just, knowing that x equals r cosine of theta and y equals r sine of theta, we're just going to replace for y and x. So we have 4 times r sine theta squared equals, instead of x, we say r cosine theta. Okay, So then let's distribute this power into each term. We have 4r squared sine squared theta equals r cosine of theta. And then let's move everything to the left. Because writing an equation from, converting an equation from Cartesian to polar, usually it means to write a polar equation in terms of r. I mean, r equals in terms of theta is what I meant. So we say r equals something in terms of theta, and that will be our polar equation. So that's our objective, to write all of this in terms as r equals an expression in terms of theta. Okay, so we have 4r squared sine squared theta minus r cosine theta equals 0. Right? So what else can we do here? We can factor out r. So r factored out, we have 4r sine squared theta minus cosine theta equals 0. Right? So in this case, we have, when would this equation be true? Either when r equals 0 or this entire thing is 0. Right? So let's write that down. So either r has to be equal to 0, right? Or we have to have that expression 4r sine squared theta minus cosine theta equals 0. So this is not much of a polar equation. So let's use this for our purpose. So let's see how far we can get with this. So let me solve for r using this equation. Cosine of theta, and then r would be equal to cosine of theta divided by 4 sine squared theta. So let us, I guess we can leave it like this, but it's better if we can get something without power. So let's do that. So we have, let's open this up a little bit. So we have r equals cosine of theta divided by sine theta times 1 over sine theta again, right? So far we're okay, and we need this 4 in the denominator times 1 over 4. Okay. Now, cosine over sine is cotangent. 1 over sine is cosecant. So let's recall. Let me. Recall that the cosine theta divided by sine theta is equal to cotangent of theta, and then 1 over sine theta is equal to cosecant of theta, right? We know that. So let's replace what we have, and I'm going to put this 1/4 at the beginning. So we have r equals 1/4 cotangent of theta times cosecant of theta. Okay, so this would be our polar equation right there. Okay. Let's do another example of this type, that is. So here we have this equation. Please go ahead and pause the video and see if you can find the polar equation for that, convert this Cartesian equation to polar equation. Okay, that should be pretty straightforward because we know what that is, right? That's just r squared on the left. So use that as a hint and pause the video and continue after that. Okay, so we know that this piece is r squared. So therefore, on the left, we have r squared equals 2c times, instead of x, let's put r cosine of theta. And then we have r on both sides. We want to have 1r, so on one side. So that, let me cancel this. What we have left with is simply just r on the left, and then 2c cosine of theta. Okay, so I want to put that in parentheses like that. Lowercase c and cosine. So this one was quickly converted from one form to the next. Okay. So remember in the previous section, we talked about curves that have parametric equations, and we want to find the tangent to those curves. We want to find the area underneath these curves that have been given to us with parametric equations. So here we want to find tangents to polar curves, or equations that have been given to us in polar form. Now the formula, the main formula is the same, but the details are different, of course, because we have polar components. So recall that x and y are defined as such for polar coordinates, so that they have parametric equations such as this. Okay, so r, as we saw just now with these couple of examples, r is given in terms of function of theta. So that would be r in that case. Okay, so with that parameterization of polar curves, then the method to find the tangent to polar curves, you saw this formula, the main formula, this side, for equations that are in Cartesian form, right? But now, instead of saying dy dt, which is what we did with in the previous section, we say dy d theta. Okay, and that is one subtle difference, but this is quite different than what we had with the other formula. Okay, so we're going to apply this formula. And we remember from the previous section again, horizontal tangents are located where dy d theta is equal to 0. And this goes back to basic algebra, as we learned with the linear slope formula, right? Delta y over delta x. If delta y is equal to 0, then we have a horizontal line. If we have undefined slope, we have a vertical line. So vertical tangents are located where dx d theta is equal to 0. And here's a small note for tangent lines at the pole, right? At the origin, we have r equals 0 and dy dx equals tangent of theta. Okay, so here in this example, we want to find the slope of the tangent line to the given polar curve at the point specified by the value of theta. Okay, so we're going to apply this formula to find the tangent to the curve at that point. Theta, in this case, equals pi over 3. Okay. So let us begin with that formula. We have dy, I guess, dy dx, I'll just write the formula again here. Dy dx is equal to dy d theta divided by dx d theta. And that was equal to, what was the formula? Let me see, dr d theta times sine of theta plus r cosine of theta divided by the same thing, dr d theta times cosine of theta minus r sine of theta. Okay. All right, so this was our formula. Now let's apply it. Dr d theta, right, taking the derivative of this, we have minus cosine of theta, right? That's all. So that would be minus cosine of theta times sine theta plus r times cosine theta. Now r is that whole thing. We have it. R equals 2 minus sine theta. So 2 minus sine theta times cosine of theta. Like that. Okay. Now in the denominator, it's again dr d theta. So I can write minus cosine theta here times cosine theta this time minus, once again, r, which is 2 minus sine theta times sine theta. Oops, I'm off the page again. Barely fit there. Okay, so obviously we have to simplify this, right? So let's do that here. So we have minus sine theta cosine theta, and then plus, we have plus 2 times cosine theta minus sine theta cosine theta. Right? I'm just distributing the terms. That divided by minus cosine squared theta minus 2 times sine theta. And then, of course, let's see, plus sine squared theta. Like that. Okay, is there anything else we can simplify? There sure is. Notice that these two, we can combine these two, right? This one and this term can be added up. They're the same. So minus 2 sine theta cosine theta. And of course, plus this. So I'll just put that in the middle. So we have 2 cosine theta minus 2 sine theta cosine theta. Okay, divided by, what else do we have here? Minus 2 sine theta, let's see, sine, okay, so minus, I'll start with that, minus 2 sine theta plus sine, I'll just list the sines, and then minus the cosine. Like that. So now we have to recall some of the trigonometric identities we worked with back in trigonometry, Math 127. So let me list them here. They are very, very useful. They were useful then and they're useful now. And they will be useful if you have to take the next calculus class. So we have, recall that sine 2 theta is equal to 2 sine theta cosine theta. Recall that. And also recall that sine squared theta, or cosine squared theta for that matter, so sine squared theta is 1 minus cosine 2 theta over 2, and cosine squared theta is equal to 1 plus cosine 2 theta over 2. Okay, so this is the identities we're going to use here, and we're going to substitute for these. So this one is going to be written more compactly as sine, instead of minus 2 sine theta cosine theta, it's going to be minus sine 2 theta. And then we're going to replace these two with these equivalents. So we have 2 cosine theta. And this is, by the way, of course, I forgot to write, these are all dy dx, right? We're calculating dy dx here, dy dx, and then, of course, this one also is dy dx. So 2 cosine theta minus sine 2 theta divided by minus 2 sine theta plus, instead of sine squared theta, I'm going to plug in this one, plus 1 minus cosine 2 theta over 2 minus, instead of cosine squared theta, this whole thing. Minus 1 plus cosine 2 theta divided by 2. How do I know to do this? It's just the more you work with these things, the more you'll know which way you have to go with these to simplify them. That's all. And then let's see. So now we have to take the common denominator, simplify this. What we have here. So let's do that. So do I want to, maybe I can put another line there. So let me try putting that here. dy dx is equal to, so we have 2 cosine of theta minus sine 2 theta, like that, minus 2 sine theta. Let's take the common denominator here, which, so we have 1 minus cosine 2 theta minus 1 minus cosine 2 theta, like that. Okay, then let's, on the next page, let's simplify this a little more. Okay. So notice that these two, positive 1 and negative 1, add up to 0. So we will have dy dx equaling 2 cosine theta minus sine 2 theta divided by, we have minus 2 sine theta plus minus cosine 2 theta and minus cosine 2 theta. So we get minus 2 cosine 2 theta divided by 2. This is nice because now we can cancel the 2's and avoid having a complex fraction. So let's do that next. And so we have, well, we don't need that anymore. So we have minus 2 sine theta minus cosine 2 theta. So this is our simplified slope formula, right? This is, let's make a note of that. Okay, so now when we were told that theta, we have to find the slope when theta is pi over 3 for this polar equation, right? Or polar curve. So when, let me move this up a little bit. So when theta equals pi over 3, then we have this whole equation, or the slope equation, dy dx equals 2 cosine. Wherever we have theta, we'll replace with theta with pi over 3. So pi over 3 minus sine 2 times, sine 2 pi over 3, and divided by minus 2 times sine pi over 3 minus cosine of 2 pi over 3. Okay. This is again having taken having taught the trigonometry last semester. Things are fresh in my mind. So for cosine pi over 3, we have positive 1/2. 2 pi over sine 2 pi over 3, that's the second quadrant. This is positive. Sine is positive in that quadrant. So positive square root of 3 over 2. Sine of pi over 3, that's in the first quadrant. It's positive. It's square root of 3 over 2 again. Now cosine in the second quadrant, which is where this is, 2 pi over 3, is minus 1/2. So let's substitute for these. So we have dy dx equals 2 times cosine pi over 3 is 1 over 2 minus sine of 2 pi over 3, that's minus square root of 3 over 2 like that, and then minus 2 times sine of pi over 3, that would be square root of 3 over 2 minus cosine of 2 pi over 3, that is minus 1/2, right? So minus again minus 1/2. Okay. So I should clean this up after recording this video. Okay, so we have dy dx. So we have 1, 2 times 1/2 is just 1, minus square root of 3 over 2. This is minus square root of 3 and plus 1/2. Okay, so then we get a complex fraction, right? We have common denominator 2 minus square root of 3 divided by minus 2 square root of 3 plus 1, and so we have these two cancel each other out. We get, what do we get? We get dy dx equals 2 minus square root of 3 divided by minus 2 square root of 3 plus 1, or 1 minus 2 square root of 3. Like that. Okay, so that's that one. Let's do another example of the same kind. Here it is. Maybe it's a good time now to again pause the video and see, solve this on your own and find the slope of the tangent at theta equals pi. Okay, so I hope you get our answers agree at the end. Okay, so we begin again with the formula that we have. dy dx is equal to dy d theta divided by dx d theta, which is equal to dr d theta sine of theta plus r cosine theta divided by dr d theta cosine of theta minus r sine of theta. Okay, so let's find each of these terms. We have dy dx. So dr d theta is 1/3, right? 1/3 times minus 1/3 sine of theta over 3. Okay, so we have minus 1/3 and sine of theta over 3, that's dr d theta, times sine of theta. So sine of theta plus r is that cosine of theta over 3 times cosine of theta. Now, in the denominator, dr d theta, it's again that whole thing. So minus 1/3 sine of theta over 3, this time times cosine of theta, minus r, which is that whole thing, or this, cosine of theta over 3 times sine of theta. Okay. So now, when theta equals pi, we can just substitute, right? So we get pi over 3 here, pi over 3, pi over 3, pi over 3. So we can substitute immediately. So when theta equals pi, we have the following. Okay, we have dy dx equals minus 1/3 sine of pi over 3 sine of pi with this one, sine of pi plus, you already know this term is going to be 0, right? Sine of pi is 0 times all of that. That term will drop out eventually. So cosine of pi over 3 times cosine of pi, in the denominator minus 1/3 sine of pi over 3 cosine of pi minus cosine of pi over 3 sine of pi. Okay, so all right, so let me make this a little bit. So dy dx, all of this drops out because of that. Sine of pi is 0, so multiply by that. So we get 0 there, plus cosine of pi over 3 is 1/2. So cosine of pi is minus 1. minus 1/3. Sine of pi over 3 is square root of 3 over 2. In the first quadrant, that would be positive. So square root of 3, positive square root of 3 over 2. Cosine of pi, again, minus 1. Minus sine of pi, once again, it's 0. Multiplies by this, we get 0. Okay, so this simplified much quicker than the previous example. Dy dx, so we have minus 1/2 divided by, so we have minus times minus is positive, square root of 3 over 6, right? So positive square root of 3 over 6. We have this complex fraction. We can simplify this. So we end up with minus 6 divided by 2 square root of 3. And then next we will get minus 3 over square root of 3. And so, or no, sorry. I will clean this right now. Let me do that. But I will clean this before posting the lecture notes on Canvas. But this should be equals minus 3 over square root of 3. Of course, we want to rationalize this. So we have times square root of 3 over square root of 3, and then we have minus 3 square root of 3 over 3, and then these cancel out, and we end up with minus square root of 3. Okay, so the slope of that polar curve, the slope of the tangent to that polar curve at theta equals pi is that. Okay. All right, so next, let's do an example of this kind, which is find the points on the given curve where the tangent line is horizontal or vertical. So we know that for a tangent line to be horizontal, then dy d theta has to be 0, right, for this to be true. And for the tangent to be vertical, then dx d theta has to be equal to 0. So in each case, that's what we'll be looking for. For this case, we will calculate dy d theta. We know how to do that, right? This is how. So that's dy d theta. That's our formula. Dx d theta, it's that formula. So we're going to get we're going to take each piece of this formula and see where that piece is equal to 0. That will give us the horizontal tangent. We're going to look at where dx d theta piece is equal to 0. That'll tell us where the vertical tangents are, the points where the vertical and horizontal tangents are. Okay, so that's the plan. So I think you might want to pause the video at this point because we worked with these formulas just now, and give it a shot, see, and come up with your own solution. Okay, so what I will do is first look for where the horizontal tangents are located. So I'll start with calculating dy d theta. So dy d theta is, our formula was dr d theta, sine of theta plus r cosine theta. Okay. So dr d theta will be that, minus 3 cosine theta, minus 3 sine theta, times sine theta right there. So sine theta plus r, which is 3 cosine theta, times cosine theta, so we have minus 3 multiplying, we have minus 3 sine squared theta plus cosine 3 cosine squared theta. Like that. And then so these are sine squared and cosine squared, and we've learned, one of the things you learn in working with these over and over, that it greatly simplifies these expressions if we replace these with their equivalent as 1 minus cosine 2 theta over 2, and for this one as 1 plus cosine 2 theta over 2. So let me just make a mention of them here. Recall that sine squared theta is equal to 1 minus cosine 2 theta over 2, and cosine squared theta is equal to 1 plus cosine 2 theta over 2. Okay, so replacing that with these two, we have dy d theta is equal to minus 3 times all of this, 1 minus cosine 2 theta divided by 2, plus 3 times 1, that the equivalent, which is that 1 plus cosine 2 theta divided by 2. Okay, now let's distribute the minus 3 and 3. So we will have minus 3 plus 3 cosine 2 theta over 2 plus 3 plus 3 cosine 2 theta over 2. The denominators are common. Of course, we can then combine the terms that we can. In the numerator, right off the bat, minus 3 and 3 can add up to 0. So we end up with dy d theta equals 6 cosine 2 theta over 2. Over 2, which is of course 3 cosine of 2 theta. Okay. So horizontal tangents, therefore, if that's dy d theta, the horizontal tangents are where this expression, when this expression is equal to 0, right? So let's make a note of that. Horizontal tangent is where 3 cosine 2 theta equals 0. Okay, so then cosine 2 theta is equal to 0. So this means that cosine of 2 that 2 theta must be either equal to pi over 2 or 3 pi over 2. So 2 theta must be equal to pi over 2 or 3 pi over 2. We're looking for theta, so theta would be dividing both sides by 2. So we have theta equals pi over 4 or 3 pi over 4, right? So that's for theta, but we want the points on the curve where we have horizontal tangents. So we need to calculate that. So thus, that's given this equation that we have in from the beginning, r equals 3 cosine of theta, are at, so let's calculate them. So we're just gonna, since we know the angles, those two angles, we're gonna plug in and calculate the r, which would be the other component of the point, right? R comma theta. So then r equals 3 times cosine of pi over 4. Of course, this is square root of 2 over 2, so this would be 3 times square root of 2 over 2. So that means that r is 3 times square root of 2 over 2 comma pi over 4 being the theta. Okay, so that's one of the points where we have the horizontal tangent. Then let's find the horizontal tangent, which happens when theta equals 3 pi over 4. So 3 pi over 4, that's in the second quadrant, and where cosine is negative, negative square root of 2 over 2. So 3 times negative square root of 2 over 2, and we end up with minus 3 times square root of 2 over 2. And so the other point where we have horizontal tangent is minus 3 times square root of 2 over 2 comma 3 pi over 4. Okay, so that's another point. Like that, and also that one. All right, I hope this is making sense. I hope this is agreeing with what you wrote down. Now we have to look for the vertical tangents for the same polar equation. Let's do that here. So the vertical tangent is where dx d theta is equal to 0, right? So given, since we need to have that in front of us, this is our polar equation. Given r equals 3 times cosine of theta, we have then dx d theta is dr d theta times cosine of theta minus r times sine of theta. Okay, so let's see, dr d theta, again, it would be minus 3 times sine theta. Cosine theta is cosine theta, minus r is 3 cosine theta. Let's see, minus 3 cosine theta times, let's see, times sine theta. Okay. All right. So now let us simplify here. What do we have? Oh, well, so these are the same thing, right? Minus 3 times sine theta cosine theta minus 3 times cosine theta sine theta is the same thing. So we have, what we have here is dx d theta and dx d theta is equal to minus 6 sine theta cosine theta, right? So let's just kind of rewrite this in factored form, right? So I will do that. Dx d theta is equal to minus 3 times 2 sine theta cosine theta. And of course, we do this because now we have a formula for that. So we can rewrite this in more compact form. So recall that you've seen this applied before. Sine of 2 theta equals 2 sine theta cosine theta. Okay, recall that. And so instead of that, we say minus 3 times sine 2 theta. So dx d theta is minus 3 times that. So we're going this way, sine 2 theta. Okay, so now we know that we have vertical tangents wherever this quantity is equal to 0. We have that quantity. Let's set it equal to 0 and solve for theta. So we have minus 3 times sine 2 theta equals to 0. That means 2 theta is equal to 0, or where else do we get sine of some angle equal to 0? Pi, right? So, or 2 theta must be equal to pi. So we're looking for theta, which means from this equation theta must be equal to 0, or from this equation theta must be equal to pi over 2. Okay. So thus the vertical tangents are located at these points. So let's calculate for theta equals 0 and for theta equal pi over 2, we will calculate the r value. So when theta equals 0, r equals 3 times cosine of 0. 3 times cosine of 0 is 1. We get 3. So therefore we have the point. So this is r, which means the point at which we have this vertical tangent is 3 comma theta being 0, right? 0. The other one happens when theta equals pi over 2. So when theta equals pi over 2, then r is equal to cosine of pi over 2. Of course, cosine of pi over 2 is 0. So 3 times 0, we have 0. So that's the r when theta equals pi over 2. So we have r equals 0 at theta being pi over 2. So the vertical tangents that we mentioned are located at the points this and that. Okay, at these 2 points. Okay, so we found the locations for the horizontal and vertical tangents. Let's do another example. I encourage you to please pause the video and see and find the locations for the horizontal and vertical tangents of this polar equation. Okay? All right, so I will begin by calculating the horizontal tangents first. So we have dy d theta to deal with. Dy d theta, we have the formula for it, that dr, it's equal to dr d theta sine of theta plus r cosine of theta, like that. So dr d theta, this is pretty straightforward. It will be just e theta, e to the theta power, times sine theta, plus r, which is again e to the theta power, times cosine of theta. Okay, so now we can factor out e to the theta power, right? So we have d theta, dy d theta. So this is e to the theta power times sine theta plus cosine theta. Okay, like that. So horizontal tangents are whenever this quantity is equal to 0. So let's make a mention of that. Where dy d theta is equal to 0. So when would this expression be equal to 0? That piece will never be 0, right? E to the theta power will never be 0. So the only chance for this expression to be 0 is if this piece is equal to 0, right? So because e to the theta will never be 0, then let's find out where this expression is equal to 0. So sine of theta plus cosine of theta equals to 0, and that'll be that's sine of theta equals minus cosine of theta, or in other words, sine of theta divided by cosine of theta equals to 1. And of course this is tangent of theta, right? Sine divided by cosine is tangent theta. So if, which means tangent of theta equals -1. So if tangent of theta equals -1, then the points we can have where when this happens, in terms of positive angles, meaning moving in the counterclockwise direction. So where we have, so one of the components has to be negative. This happens in the second quadrant. So that would be when theta equals 3 pi over 4, and also happens in the fourth quadrant, which is when theta equals 7 pi over 4. Okay, so more generally we can write this as pi over or minus pi over 4 plus n pi, like that. Okay, so if we, for example, if you, and of course n is any integer. So now if n equals 1, so I guess what I'm saying is that this is the general case for all of these angles that will make that, that will give us the horizontal tangents, for which dy d theta is equal to 0. So if n equals 1, that would be pi minus pi over 4, which will give us 3 pi over 4. If n equals 2, 2 pi minus pi over 4, that will give us 7 pi over 4. So this is a general case. It'll go through all those points for which the original equation has horizontal tangents. Okay, so we can use that rather than these individually. We can use that as a more general equation for where or which points have where the horizontal tangents occur. So let's make a mention of that. So thus, so the horizontal tangents at these. So we can simply, if this is the equation we have, right, so we have the points would be e to theta. Let's take that as the general form. So e to minus pi over 4 plus n pi, and theta would be itself. So, oops, sorry, I was too low on the screen. So this being our equation again, r would be e to that theta value right there, and theta would be that. And this is again the general all angles, or r angles theta, for which we have that, where the horizontal tangents are located. So we have minus pi over 4 plus n pi. Like that. It's not incorrect if you just give e to the 3 pi over 4 comma 3 pi over 4 and e to the 7 pi over 4 comma 7 pi over 4. Okay, as a matter of fact, let me add that. Or if you want to give it more specifically, or more specifically, I want to keep that on the screen, or more specifically, we have e to 3 pi over 4, comma 3 pi over 4, and e to 7 pi over 4, comma 7 pi over 4. Okay, like that. All right, so now let's look for the vertical tangents. So we have to calculate dx d theta and see where that is going to be equal to 0. So dx d theta will be equal to 0 for such cases. So dx d theta and is equal to this, dr d theta cosine of theta minus r sine of theta. Now let me rewrite the equation so we have it in front of us, even though it's a simple equation like that. All right, so we have dx d theta equals dr d theta is itself times cosine of theta minus r, which is itself e to the theta times sine of theta. Right, so once again we can factor out e to the theta. Just like before, so we're looking for when this expression is equal to 0, right, this expression. So just like before, we know that e to the theta will never be 0. So then, let me add a comment here about that. Since e to the theta is never 0, then we must have for it to be any vertical tangents we should have this piece equal to 0. Then cosine of theta minus sine of theta must be equal to 0. And then if we sine of theta, and then so when do we have this situation occur? When do we have cosine of an angle equal the sine of the same angle? The quick response is pi over 4, right? But are there other angles that have the same situation? And the answer is that yes. So we have, so so based on this, let's generalize that. So we know that theta is equal to, we must have theta equals pi over 4, right, in the first quadrant. Then we can generalize this by adding pi to it. So pi over 4 times 1 pi, pi over 4, not times, sorry, plus. Pi over 4 plus pi, pi over 4 plus 2 pi, pi over 4 plus 3 pi, and so on. So let's generalize that to pi over 4 plus n pi, and n any integer, right? So we can do that, and that will give us, let's see, so that will give 1 pi, that would be, well, n, if n is 0, we get pi over 4. If n equals 1, I'm just going through the positive integers, pi plus pi over 4, that would be in the third quadrant, and then 2 pi, or, right, 2 pi plus pi over 4, that will be again in the first quadrant. So what we will get from this is the first quadrant and the third quadrant. So I'll write it here. So this is generalizing, this one is generalizing the first and third quadrants. I mean, all their answers in the first and third quadrant. Okay, those are the theta values for which this equation will hold true. So then, so the vertical tangents occur at, we can write that as r would be e to the theta power, right? R is that. So e to that generalized angle for where the vertical tangents are. So pi over 4 plus n pi. And then comma, that angle, pi over 4 plus n pi, r comma theta. like that. So if you want to give this more specifically, it'll be pi over 4 and pi, and then 5 pi over 4. Sorry, I think earlier I said 3 pi over 4. I apologize. It's pi over 4, and in the third quadrant it would be 5 pi over 4. So let me add that more specifically. Or at theta equals pi over 4 and 5 pi over 4. And so let's write that here. So e to pi over 4 comma pi over 4 and e to 5 pi over 4 comma 5 pi over 4. So these are specific points on the curve, and that's generally speaking. Okay, I hope this discussion has been useful to your understanding of this material in this section. And I thank you for watching the video until this point. And for now, have a nice day, and I'll see you again next time.